This is a quick overview of the architecture and main functionalities of Frame Modeler 2D. FM-2D platform is an open source computational platform that has been developed entirely in MATLAB, and it's meant to streamline and expedite the process used by structure engineers and researchers for modeling and analyzing steel frame buildings in open seas using state-of-the-art modeling guidelines. The platform can be downloaded, including the installation file and the source code, directly from GitHub at the link shown below. So this is a brief overview of the operational procedures in FM-2D, which can be divided into three distinct parts. First, there is the user definitions, basically the user input, which is done through the graphical user interface, the GUIs, which includes a definition of the numerical model parameters, the building parameters, and the analysis parameters. The second set of operations is the FM-2D background operations, which includes the characterization of the different member and spring behaviors and the construction of the numerical model in OpenSeas, and running the actual analysis procedures and reading the output data from OpenSeas, the recorder data, and processing it. And the last set of procedure are the back-end procedure. Basically, these are the output that can be accessed by the user with respect to the visualization of the analysis output or reporting it in text files. So here you can see the main console of FM-2D, which includes three main panels. The first panel is the project file management, where you can start a new project, open an existing project, or save it in a different location, as you would typically do with any other software. The second panel is the project definition panel. This is where the user would input and define the three main components of any project, including the model parameters, the building parameters, and the analysis parameters, as discussed previously in the operational procedures. The last panel includes some buttons that will initiate the execution of the analysis code and for visualizing and reporting the data. Also in the console at the bottom over here, you have the progress status bar, you have a reset button, you also have at the top, you have a button for developers, and here you can access an interface for that aims to aid developers for understanding the code hierarchy and interdependencies, as will be discussed by the end of this presentation. There is a button for registering, for receiving updates and news for FM-2D. There is also a help button that will open the manual and will give you access to the YouTube video tutorials. So from the main console, the user can access different GUI modules in order to define the three main project components, the model parameters, the building and analysis parameters. From each button, the user will get a different separate module as shown here. Each one of these modules contain a number of tabs from which the user will need to fill a number of fields, select a number of checkboxes and other selections from drop-down menus, basically to define the different parameters and specifics of the building being analyzed. Regarding the employed modeling methodology, here you can see a plan view of a generic building. The building includes some lateral load resisting systems in each of its orthogonal directions. Those here are labeled as main frame or MF. The rest of the building is being supported by a gravity framing system, GFS, and this gravity framing system typically include a number of gravity columns, gravity beams that are connected together with gravity connections. When analyzing or representing this building in 2D for a given direction, which labeled here as the considered direction, one of the orthogonal directions of the building. This is represented as follows. One of the main frames is modeled as shown here, while the rest of the building, that is the gravity framing system, is modeled using an equivalent gravity frame, which is the general case for the leaning column concept. The equivalent gravity frame is linked to the main frame using some floor links as shown in red. In the current version of the platform, buildings with moment-resisting frames and concentrically braced frames, MRFs and CBFs, are currently supported. These two systems are idealized mainly using the lumped plasticity approach as shown here, using a combination of elastic elements and nonlinear rotational springs. The more details can be found in the manual. To go through the main features of the FM-2D platform quickly, probably one of the most time-consuming things when modeling is defining the building geometry and the member sizes. For that purpose, in order to expedite this process, in FM-2D, this is first done externally using a single pre-formatted Excel file as shown here that includes a number of pre-formatted sheets, and inside each sheet you will need to provide the corresponding data, like as I'm showing here. For instance, this is how I define the main frame column and member sizes at different stories and at different axes. To aid with this definition, there is already in the Excel file, there is an integrated databases for the European and American cross sections, where you can select directly from it the type of cross section for the different beams and columns and braces in your model. With respect to the modeling basic considerations, there are many options that you can choose from, and key contributions that you can consider in your numerical model. This includes the consideration of the composite action effect that's being provided by the floor slab, and how will this composite action affect the beam and the connections behavior. So this can be considered in FM-2D using state-of-the-art recommendations. You can also consider or ignore the panel zone shear deformations while considering or ignoring the composite action effect. As well, you can consider the strength and stiffness that's being provided by the gravity framing system and the gravity framing connections. So this can also be considered in the model using state-of-the-art recommendations as discussed in detail in the manual. Also, the user has full control over the type of supports and connections being used in the model. For instance, you are able to control the column base support condition between pinned, fixed, and exposed column base connections. You can control the type of the column splice between pinned and rigid, and you can also control its location within the height of the story. You can control the floor diaphragm in plane movement, as well as the braced frame beam sagging. So these are all options that are available to select from. You can also control the diaphragm floor to the main frame connection flexibility by tuning in the strength and stiffness parameters of the floor links attaching two systems together. When it comes to loads, you have up to 4 different floor and facade area load cases that you can define. You can control the load value at typical and roof levels. You can control the load combination coefficients that are used to compute the seismic weight and the mass. When defining materials, FM-2D has integrated database for material properties that covers all the main steel types and grades in Europe, United States, and China, as shown over here. With respect to the analysis, FM-2D offers 6 types of static dynamic analysis procedures to be conducted. The first is the eigenvalue analysis, and from that you can get the eigenmode periods, the eigenmode vectors, and the modal mass participation factors. You can also conduct static pushover analysis, where you push your structure monotonically to a target drift ratio using pre-specified mode pattern. You can also conduct static equivalent lateral force analysis, or ELF analysis, where you apply statically some profile of lateral forces at different floor levels to your structure, which can help when you are conducting some kind of design procedures based on the design code. You can also conduct incremental dynamic analysis, or IDA, where you evaluate the structural response at different seismic intensities that are traced up till collapse. You can conduct 2 types of dynamic analysis, of course, using a set of ground motion records. You can scale these ground motion records using a constant scale factor, or alternatively, you can scale these ground motion records to a target seismic intensity. You are also able to consider the modeling uncertainty using a Monte Carlo simulation, and this is all done within FM-2D. The only thing that you will need to provide is basically the logarithmic standard deviation, or the uncertainty associated with the modeling parameters of the different component models for the beams, the columns, the panel zones, and everything pretty much. You can also control the modeling uncertainty associated with some material parameters, the damping coefficient, even with the mass and loads inside your model. For visualization, starting from the execution of the analysis, you are able to visualize and monitor the global engineering demand parameters in your model. This includes the story drift ratio and the peak floor acceleration, and those you can visualize while the analysis is being conducted, which is very useful when you are running a long analysis that involves a large number of ground motions. So FM-2D will provide you of live plots of these main ADPs and how the peak values change with different ground motions. In the same time, if you're running incremental dynamic analysis, you will see the incremental dynamic analysis data for the story drift and the peak floor acceleration, which can be very useful in tracking the behavior of the structure while the analysis is being conducted. When the analysis is concluded, you are able to visualize pretty much all the global engineering demand parameters in your model. Here I'm showing some of the plots that can be generated. This includes the base shear versus drift. So different types of plot, you can see it here from dynamic analysis or from pushover analysis. If you conduct a Monte Carlo simulation, you can see the scatter of the different engineering demand parameters with respect to the realization number. You can visualize the fragility functions for the different EDPs. You can visualize the different profiles for the different EDPs, including the story drift, the residual drift ratio, the peak floor acceleration and velocity, and story shears. You can visualize the eigenmode patterns for incremental dynamic analysis. You can visualize the IDA curves, and you can visualize as well the collapse fragility curve, and you can get the distribution parameters of the collapse fragility curve. Looking at local EDPs, FM-2D provides you with an interactive interface as the one which is the one shown here, where you can pretty much explore the different elements and springs in your model interactively using those drop-down menus, and you can see here plots of the local responses of these elements and springs, and you can also save these whatever being plotted over here into text files such that you can use it externally. You can also visualize and report a collated summary of the project definitions so that you can keep track of the different analysis cases that you run. For using FM-2D, there are different ways of using it depending on your preference. If you want just to use FM-2D, you can simply download the installer file from GitHub, install it on your PC, run FM-2D using the generated executable, as you would typically do with any other software. The other thing is if you want to use FM-2D and you also would like to modify perhaps the source code to play a little bit with some of the modeling assumptions and some of the specifics of the source code. In that case, you can download directly the entire source code from GitHub directly to your PC, and then you can run FM-2D in MATLAB from your PC by running this root file, which is the graphical user interface for the main console. The third option, if you would like to use it, modify it, and also collaborate any changes that you do to the source code with other users. In that case, if you are familiar with the GitHub environment, then you would need to fork or basically download the source code using your GitHub account and perhaps through the GitHub desktop application. Then again, you can run FM-2D in MATLAB, and then you can modify the source code, and any modified files you can commit these changes to the master repository online, and at the same time you will be able to receive any code updates from the master repository whenever they are released. So the FM-2D source code can be divided into four main file types. The first is the MATLAB interface files, and those have the extension .mlapp, and these are basically the graphical user interface GUI files that control the user data input and from which the calling procedure for the different MATLAB scripts will be initiated. The second type is the MATLAB script files, .m files, and these are the primarily source code files. These are the function files that are responsible for constructing everything from the OpenC's script for the numerical model, from running the analysis and processing and visualizing the analysis data. The third type is the MATLAB data files, .mat, and these files store the metadata for the integrated databases. Right now, there are .mat files included with the source code that includes the geometric properties for the steel cross-section catalogs and for the material mechanical properties. The last type of files is the OpenC subroutine files, or the procedure files that have an extension .tcl or tcl files. So these files are called or will be sourced by the main OpenC's numerical tcl file, and these different procedures are used to construct everything from fiber cross sections to elastic members to creating nodes and springs and defining the analysis parameters. Knowing the main file types, you would also like to know how these different files and scripts depend on each other. So from the main console, by clicking on the button called Developers, you will have access to this interface. And this interface pretty much can let you inspect the code hierarchy and the variable definitions. So from the tab on the left over here, you can look at the code hierarchy and this code tree and the dependency of each script and function file on the other files in the source code. So this make it much easier if you would like to modify something. This can let you know how to modify it and what portion of FM-2D would it affect. And you would get, once you select any part of this tree, you would get a description of what it does over here. The other tab, you can go see a list of all the variables used in FM-2D and their type, whether they are a vector, array, scalar values, and so on, and where are they defined, which parent module or function where they are defined, and you are getting a short description of what each variable represents. So this again makes it easier for you to modify these variables or add something new to the code. Finally, there are step-by-step tutorials for some practical examples, including these two shown over here for a 6-story CBF building and a 4-story MRF building that you can watch in YouTube. There is a dedicated playlist at this link, and this goes through pretty much all the steps from A to Z, and it should get you started with becoming familiar with FM-2D and how to define a project and visualizing the results. Thank you for listening.